Today we're looking at the sums and the products of the zeros of a couple of different types of functions. We're going to look at quadratics, cubics, and quartics. So we'll start with the quadratics. We know what these look like. They've got x squared as their highest power of x, and they've got the shape of a parabola. And we've seen them in this form, which we call general form, where a, b, and c are just constants. A can't be 0 because if it was, we wouldn't have any x squareds and it wouldn't actually be a quadratic. And we're comfortable knowing that we can have it in this form and we may be able to factorise it. If we can factorise it, we're going to be able to see straight off what the zeros are. So here, we've explained that if our quadratic has zeros of alpha and beta, we've already mentioned that the leading coefficient is a. But if we know what the zeros are, then that actually helps us factorise it because we know that one of the factors must be x minus alpha and the other one x minus beta. And this is something that we're very familiar with. Even back at the start of the year, we knew that if we saw something like, say, this, then we could graph it nice and easily. We would say that that is an upright parabola and it has zeros at -1 and 3. And so we can sketch it nice and quickly like that. So this concept of the zeros is not new. -1 and 3 I get because it's the number here that makes this equal 0 and the number that can go here that makes this equal to 0. Now, much as we're comfortable seeing our polynomial or our quadratic function written like this or written like this, what we're going to do today is actually equate the two and compare them so that we can come up with some general rules about the sum and the product of the zeros. Now, the first thing to do is actually just to expand this expression here and reason that if these two are the same, then we should be able to equate the coefficients. So let's go ahead and expand this out. We'll do it one step at a time. We'll do a multiplied by all of this, and we'll use our FOIL method here to expand our brackets. So we've got minus alpha x, and we've got minus beta x, and we've got plus alpha beta, because we've got a negative multiplied by negative, we get all of that. And then expanding out further, we get a x squared minus a alpha x minus a beta x plus a alpha beta. All right, now if p of x is equal to all of this, but I've also reasoned that because the leading coefficients are the same, if this thing has zeros, and even if I don't know what they are, I should be able to write it like this, it stands to reason that all of this part must equal all of that part. So that's what I'm going to do next. I'm going to equate the two. I'm going to say ax squared plus bx plus c must therefore equal all of this. Minus a alpha x minus a beta x plus a alpha beta. Now if I want to equate the coefficients, it makes sense to sort of group how many x squareds and x's and constants I have. They're already nicely written on this side, but factorising this side a little bit more makes sense so that I can clearly see how many x's I've got. So if I factorise this side, I'm going to just factorise, and I mean just this section here, I can see that both these terms have minus ax in them. So I'm just going to bring that out the front to make life a little bit easier, and I can see that what's left is alpha plus beta, okay? And then I'm going to rewrite the rest. And this side can just be rewritten as it was. Okay, now I should be able to line up what is equal to what. So I can see that the number of x squareds I have on both sides is the same. So I'm learning that a equals a. Well, that's no real surprise. That's easy and obvious. But the other thing that's more helpful is that the number of x's I have on this side must be the same as the number of x's I have on this side. Now, how many x's have I got here? Well, if I wrote this a little bit differently so that the x is at the end, and I wrote it like this, alpha plus beta, you would say that I had this many x's, wouldn't you? That many x's must equal b. Now let's write that down and see if we can make sense of it. Minus a, alpha plus beta, has to equal b. And we can tell that because the number of x's hasn't changed. And if we've got b of them over here, and we've got minus a, alpha plus beta of them over here, those two things must be equal. Now, what are we going to do with that? Well, let's come up with something that tells us about the sum of the zeros. If my zeros are alpha and beta, what I've got here is a little expression for the sum of alpha and beta, and that might be handy to know. So to get alpha plus beta by itself, all I need to do is divide by negative a on both sides. and I'm going to get this. Now, if you're dividing by a negative, we know that a negative fraction can have its negative down the bottom, it can have it up the top, or it can have it just hovering out the front, minus b on a. All those three things are exactly the same. So I've come up with my first sort of rule for the lesson, one that's important. I'm going to put an important box around it because this is one that I want to remember and know. Now, I equated the x squareds. That didn't really tell me much. I equated the x's, and that gave me a lovely expression for the sum of the zeros. What happens when I equate the constants? Well, I can see that c must equal a alpha beta. Let's write that one down too. C equals a alpha beta. Now, alpha and beta, what are they again? They're my zeros. Right, so here I've got my zeros multiplied together. Could I get that expression by itself? Alpha beta equals something? Of course I could. I could divide both sides by a. And on this side I'd have c over a equals alpha beta. I'm going to write it the other way around. Alpha beta is c over a, and that's my second rule that I've just discovered. Now, you'll need to be able to generate a proof like this if required, but it's really not too hard. All we had to do was expand our brackets, group up how many x's that we had, and in fact, this line here, I could have rewritten all of that, and all of that, I just modified that section because that was the bit I needed. And then I equated the coefficients. One was boring, but two of them gave me an interesting fact. So how do we use this fact? Well, I can use these facts as yet another clue to help me when I'm factorising my polynomials. So this is just another hack, if you like, another tool that we've got in our toolkit. So this example explains how it might help us. Show that x equals 5 is a zero of this polynomial. Okay, so this is not related to today's lesson, this is related to the last couple. How do we do that? Well, we find p of 5, because if 5 is a zero, then when we find p over 5, the answer should be 0. So subbing it in, I'm only doing it once, so I won't put it in as a formula into my calculator. I can probably do this in my head. I've got 3 times 5 squared. 5 squared is 25, 3 of those is 75. And then I'm subtracting 35s, so I'm subtracting 150, and then I'm adding 75. And I can see quite clearly that I've got 75 plus 75 is 150, subtracting 150, and that's 0. So there we go, I've shown it. All right, B, use the sum of zeros to find the other zero. All right, well, the sum of zeros is always negative b over a. Now, what is negative b? What is a? This is assuming that we have our polynomial written in this form. So the b is the number of x's you have. The c is the constants. So in this polynomial here, I can see that my a is 3, my b is negative 30, and my c is 75. So straight away, I know that the sum of the zeros will be negative b on a, negative 30, well that's just 30, isn't it, over a, which is 3. 30 divided by 3, well that's 10. So what we can see here with this really simple formula is it's really nice and easy, without even factorising this thing, to look at a, b and c and use their values to say, hey, the two zeros add up to 10. So if I know what one of the zeros is, 5, what's the other one? Must also be 5, because 5 plus 5 is 10. How would you set this out? Well, there's lots of ways. I think I would probably write all of this. You could perhaps jot that down too, but the more of these that you do, you're going to automatically know what A, B, and C are, and you'll just jump to the one that you need. So I would say alpha plus beta equals 10. So if we say one of the zeros, if alpha equals 5, then beta must also be 5. And that is a perfectly adequate way of setting it out. Now, if beta is also 5, then what do we know about factorising this thing? We know that if it sits in this form, I need a bit more space here, a x minus alpha, x minus beta, then if we've just found alpha and beta, and they're 5, then we can put those in there like that. And in fact, because these are exactly the same, we could write it even more neatly by saying it's like this. The only thing left now is to find what a is. Well, when we expand this part out, the highest term in x will be x squared, we need our leading coefficient to be 3. So clearly for this question, A is 3. And I've now factorised this without actually doing a traditional factorising method. Now let's just relate that back to something that we've already learned. We've already seen that the axis of symmetry of a quadratic function that is in this form can be found by just plugging in x equals minus b, where b is the coefficient of x, over 2a, where a is the coefficient of x squared. And this makes complete sense because, of course, if you're finding the axis of symmetry of a parabola, let's say that it has zeros here and here, and we'll call those alpha and beta, then we know that the axis of symmetry is halfway in between the x values of those 2 points. And so if you want to average something, it makes sense that you add them together. So if we call the zeros alpha and beta, we can add them up and divide by 2 to find the halfway or the midpoint. And of course, we've just learnt now that when we add the zeros together, we get minus b on a. So if we're going to halve that, we're going to get minus b on 2a. So again, something that we already knew, but relating back to something that we have just learned.